The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
During the course, we've developed a number of very powerful and useful tools, and we've seen how these can be used in designing and analyzing systems, for example, for filtering, for modulation, etc. I'd like to conclude this series of lectures with an introduction to one more important topic, namely the analysis of feedback systems. And one of the principal reasons that we have left this discussion to the last part of the course is so that we can exploit some of the ideas that we've just developed in some of the previous lectures, namely the tools afforded us by Laplace and Z-transforms. Now, as I had indicated in one of the very first lectures, a common example of a feedback system is the problem of, let's say, balancing a broom, or in the case of that lecture, balancing my son's horse in the palm of your hand. And kind of the idea there is that what that relies on in order to make that a stable system is feedback, in that particular case, visual feedback. That specific problem, the one of balancing something, let's say, in the palm of your hand, is an example of a problem which is commonly referred to as the inverted pendulum, and it's one that we will actually be analyzing in a fair amount of detail, not in this lecture, but in the next lecture. But let me just kind of indicate what some of the issues are. Let me describe this in the context not of balancing a broom on your hand, but let's say that we have a mechanical system which consists of a cart, and the cart can move, let's say, in one dimension, and it has mounted on it a bar, a rod, with a weight on the top, and it pivots around the base. So that essentially represents the inverted pendulum. So that system can be more or less depicted as I've indicated here. And this is the cart that can move along the x-axis. And here we have a pivot point, a rod, a weight at the top, and then, of course, there are several forces acting on this. There is an acceleration that can be applied to the cart, and that will be thought of as the external input. And then on the pendulum itself, on the weight, there is the force of gravity, and then typically a set of external disturbances that might represent, for example, air currents or wind or whatever, that will attempt to destabilize the system, specifically to have the pendulum fall down. Now, if we look at this system in more or less a straightforward way, what we have then are the system dynamics and several inputs, one of which is the external disturbances, and a second is the acceleration, which is the external acceleration that's applied. And the output of the system can be thought of as the angular displacement of the pendulum, which, if we want it balanced, we would like that angular displacement to be equal to 0. Now, if we know exactly what the system dynamics are, and if we knew exactly what the external disturbances are, then in principle, we could design an acceleration, namely an input, that would exactly generate 0 output. In other words, the angle would be equal to 0. But as you can imagine, just as it's basically impossible to balance a broom in the palm of your hand with your eyes closed, what is very hard to ascertain in advance are what the various dynamics and disturbances are. And so more typically, what you would think of doing is measuring the output angle and then using that measurement to somehow influence the applied acceleration or force, and that then is an example of a feedback system. So we would measure the output angle and generate an input acceleration which is some function of what that output angle is. And if we choose the feedback dynamics correctly, then in fact we can drive this output to 0. This is one example of a system which is inherently unstable, because if we left it to its own devices, the pendulum would simply fall down. And essentially, by applying feedback, what we're trying to do is stabilize this inherently unstable system. And we'll talk a little bit more about that specific application of feedback shortly. Another common example of feedback is in positioning or tracking systems. And I indicate one here which corresponds to the problem of positioning a telescope which is mounted on a rotating platform. So in a system of that type, for example, I indicate here the rotating platform and the telescope. It's driven by a motor. And again, we could imagine in principle the possibility of driving this to the desired angle by choosing an appropriate applied input voltage. And as long as we know such things as what the disturbances are that influence the telescope mount and what the characteristics of the motor are, in principle, we could, in fact, carry this out in a form which is referred to as open loop. Namely, we can choose an appropriate input voltage to drive the motor to set the platform angle at the desired angular position. However, again, there are enough unknowns in a problem like that so that one is motivated to employ feedback, namely to make a measurement of the output angle and use that in a feedback loop to influence the drive for the motor so that the telescope platform is positioned appropriately. So if we look at this in a feedback context, we would then take the measured output angle, and the measured output angle would be fed back and compared with the desired angle. And the difference between those, which essentially is the error between the platform positioning and the desired position, would be put perhaps through an appropriate gain or attenuation and used as the excitation to the motor. So in the mechanical or physical system, that would correspond to measuring the angle, let's say with a potentiometer. So here we're measuring the angle, and we have an output which is proportional to that measured angle. And then we would use feedback comparing the measured angle to some proportionality factor multiplying the desired angle. So here we have the desired angle, again through some type of potentiometer. The two are compared. Out of the comparator, we basically have an indication of what the difference is, and that represents an error between the desired and the true angle. And then that is used through perhaps an amplifier to control the motor. And in that case, of course, when the error goes to 0, that means that the actual angle and the desired angle are equal. And in fact, in that case also, with this system, the input to the motor is likewise equal to 0. Now, as I've illustrated it here, it tends to be in the context of a continuous time or analog system. And in fact, another very common way of doing positioning or tracking is to instead implement the feedback using a discrete time or digital system. And so in that case, we would basically take the position output as it's measured, sample it, essentially convert that to a digital discrete time signal, and then that is used in conjunction with the desired angle, which both form inputs to this processor, and the output of that is converted, let's say, back to an analog or continuous time voltage and used to drive the motor. Now, you could ask, why would you go to a digital or discrete time measurement rather than doing it the way I showed on the previous overlay, which seemed relatively straightforward? And the reason principally is that in the context of a digital implementation of the feedback process, often you can implement a better controlled and often also more sophisticated algorithm for the feedback dynamics, so that you can take account perhaps not only of the angle itself, but also of the rate of change of angle, and in fact the rate of change of the rate of change of angle. And so the system as it's shown there then is basically has a discrete time or digital feedback loop around a continuous time system. Now, this is an example of, in fact, a more general way in which discrete time feedback is used with continuous systems. And let me indicate in general what the character or block diagram of such a system might be. Typically, if we abstract away from the telescope positioning system, we might have a more general continuous time system, and around which we want to apply some feedback, which we could do with a continuous time system or with a discrete time system by first converting these signals to discrete time signals, then processing that with a discrete time system, and then through an appropriate interpolation algorithm, we would then convert that back to a continuous time signal, and the difference between the input signal and this continuous time signal, which is fed back, then forms the excitation to the system that essentially we're trying to control. And in many systems of this type, the advantage is that this system can be implemented in a very reproducible way, either with a digital computer or with a microprocessor. And although we're not going to go into this in any detail in this lecture, there is some discussion of this in the text. Essentially, if we make certain assumptions about this particular feedback system, we can move the continuous to discrete time converter up to this point and to this point, and we can move the interpolating system outside the summer. And what happens in that case is that we end up with what looks like an inherently discrete time feedback system. So in fact, if we take those steps, then what we'll end up with for a feedback system is a system that essentially can be analyzed as a discrete time system. Here we have what is in the forward path is basically the continuous time system with the interpolator at one end and the continuous to discrete time converter at the other end. And then we have whatever system it was in the feedback loop, discrete time, that shows up in this feedback loop. Well, I show this mainly to emphasize the fact, although there are some steps there that we obviously left out, I show that mainly to emphasize the fact that feedback arises not just in the context of continuous time systems, but also the analysis of discrete time feedback systems becomes important, perhaps because we have used discrete time feedback around a continuous time system, but also perhaps because the feedback system is inherently discrete time. And let me just illustrate one or indicate one example in which that might arise. This is an example in which is also discussed in somewhat more detail in the text. But basically, population studies, for example, represent examples of discrete time feedback systems, where let's say that we have some type of model for population growth, and since people come in integer amounts, that represents essentially the output of any population model essentially or inherently represents a sequence, namely it's indexed on an integer variable. And typically, models for population growth are unstable systems. You can kind of imagine that because if you take simple models of population, what happens is that in any generation, the number of people or animals or whatever it is that this is modeling grows essentially exponentially with the size of the previous generation. Now, where does the feedback come in? Well, the feedback typically comes in incorporating in the overall model various retarding factors. For example, as the population increases, the food supply becomes more limited, and that essentially is a feedback process that acts to retard the population growth. And so an overall model, somewhat simplified, for a population system is the open loop model in the absence of retarding factors. And then very often the retarding factors can be described as being related to the size of the population, and those essentially act to reduce the overall input to the population model. And so population studies are one very common example of discrete time feedback systems. Well, what we want to look at and understand are the basic properties of feedback systems. And to do that, let's look at the basic block diagram and equations for feedback systems, either continuous time or discrete time. Let's begin with the continuous time case. And now what we've done is simply abstract out any of the applications to a fairly general system in which we have a system H of S in what's referred to as the forward path, and a system G of S in the feedback path. And the input to the system H of S is the difference between the input to the overall system and the output of the feedback loop. And I draw your attention to the fact that what we illustrate here and what we're analyzing is negative feedback, namely this output is subtracted from the input, and that's done more for reasons of convention than for any other reasons. It's typical to do that, and appropriate certainly in some feedback systems, but not all. And the output of the adder is commonly referred to as the error signal, indicating that it's the difference between the signal fed back and the input to the overall system. Now, if we want to analyze the feedback system, we would do that essentially by writing the appropriate equations. And it's best done in generating the equivalent system function for the overall system. It's best done in the frequency or Laplace transform domain rather than in the time domain. And let me just indicate what the steps are that are involved. And there are a few steps of algebra that I'll leave in your hands. But basically, if we look at this feedback system, we can label, of course, since the output is y of t, we can label the Laplace transform of the output as y